new concept that really is based in geometry. Now, we've been dealing with a lot of things that we call scalars. We've been working with things called scalars. These are values that only require a single number. So something like time is a scalar quantity. It only needs a number. How many hours, minutes, seconds. The other thing is distance. These are called scalar quantities. How far is something? Temperature. These are what we call scalars. And you can think of some other ones as well. But these are scalar quantities. But not everything in this world can be described by a number. A scalar is nothing more than a single number. Now, some of you have taken courses in physics, maybe in high school or something else, and you learned about some other things. Things that are not scalars. Something, for example, is a force that's acting on something. It needs two numbers. It needs the magnitude of the force and its direction. These are not scalars. I'll put that as one, excuse me. Then the second one, velocity. Velocity is something that tells you how fast you're going, but in which direction are you going in? Velocity. Acceleration. Also your airflow. Air flows at a certain speed in a certain path or direction. Fluid flow. If you're looking at a river, the currents in the river, they're going at a certain speed, the speed changes in a different direction. So if we want to talk about other things in the world, we need another thing other than a single number. And that other thing we introduce is something called a vector. This is going to be a new quantitative way of describing things up to now we could not define before. Out of curiosity, I know most of you probably have, but how many people have seen vectors before? Just raise your hand and see if you've seen and are comfortable with vectors. There's a couple. Okay, so not everyone. So we will introduce those. Because we have scalars and we have something called vectors. Vectors give us two numbers to represent this thing. Something that will give us the magnitude of that force as well as its direction. So that's what we're going to cover now in 10.4, this concept of vectors. So let's start with that. This is going to now enable us to describe some more things in nature and the world around us, these concepts of vectors. Now, a vector is a quantitative object that enables us to assign both a magnitude, how much or how many, and a direction to a quantity. So as you can see, there are two numericals. We have the magnitude and the direction. We're going to find the direction using a value of theta. Now, there are two ways to define a vector. We're going to define them both ways. The first way they were defined and introduced using the geometric definition. And the geometric definition of a vector, so a vector is a directed line segment, meaning directed so it has direction, segment from point A to point B. So in essence, let's show geometrically over here. So I'm not even going to put in a Cartesian coordinate system. I'm just going to say here's my point A, and there's my point B. It is a directed line segment, so we have a direction to it, from A to B. And how do we represent that? Well, we can write it in this way. We put our points A, B, and I put an arrow over it. That's a directed line segment. If I wanted to, I could write it like that. Or we could even give it a name. We could call this a vector, and we'll look at that, vector V. Put it like that. So you could look at this, or you could just say, okay, I know what A and B is, so I'm just going to call that my vector V, V for vector. Now, sometimes in a lot of textbooks, instead of the little arrows, what you'll see is a bold V. So you see it's a really, bold, and as opposed to your normal writing. That's what is a bold V. And they won't put the arrow, you'll just see it as a bold-faced V. Okay, so that's what it is. It's a vector. Now, the length of the vector specifies its magnitude. So over here, the length of this directed line segment, so the length of the directed line segment is its magnitude. Now, if I want to find the angle, a way of talking about its direction, what you do is this is the way we're going to define it. The angle is defined as relative to the horizontal. So if I draw a horizontal line over here, I'm going to define this as the angle, or the the direction of that line segment. So theta, relative to the horizontal, defines its directions. Its direction. So geometrically, I can have lots of types of different vectors around. So you could have various vectors. I could have a vector here, call that vector U, another vector here, make that a little bit longer, call it vector V. Make a vector go horizontally, that's another vector W. So those are vectors. They all have different magnitudes, how long they are, and orientations or directions. So this vector points, downward and to the right, upward and to the right, straight across the right, or I could even go in the opposite direction if I wanted to. Those are all vectors. Unlike our scalar numbers, it requires two quantitative aspects of it to be able to define it. How long it is, the magnitude of it, and what is its orientation relative to some horizontal line. Okay, so we have these things called our vectors, if you will, geometrically. What can we do with them? Well, we can also do arithmetic with them. Just like when we define numbers, we start, well, how do we add, subtract, multiply, and do other things with numbers? We can do, up to a certain point, an element of arithmetic with vectors. Let's just show geometrically what it is. So now that we have these vectors, we can do the arithmetic with vectors. So say I have my vector, here's my vector U, and I have another vector V. And I'd like to do u plus v. How do I do that? Well, what I do is I start with vector u. Notice, these vectors are not pinned to anywhere on the board over here. I can move them around. That's what you mean geometrically. They're not tied to any coordinate system, so I can move them around. So I can start with my vector u over here. Here's my vector u. I have to roughly keep the same magnitude and direction. And if I want to add, what do? Is I simply take the arrow part of u, and link that to the beginning part of v. So I then translate this v vector down here, try and keep that same magnitude and direction. And there's my v. The resulting vector is the line I get by starting at the beginning of u and going to the end of v. So that's my new vector, u plus v. That's how I define addition. It just start with this one and then add that to it. Now, what if I did v plus u? So there's u plus v. So now let's take a look at v plus u. Well, now I would start with v over here. So here's my v. And then I'd add my u to that. So now the u goes over here in this direction. There's my u. So this is v plus u. The result is start over here and end over here. I don't have it set up correctly, but you're going to see it gives me the same type of vector. If I move this vector over here, they're the same length and the same direction. So we can show that they are, in fact, equal to each other. You can commute. It obeys a commutative property. U plus V is V plus U. But what about taking the negative of a vector? Or just subtracting a vector. Let's do the subtraction. So this is addition. Now let's turn around and look at subtraction of two vectors. So let's take our same u and v vector here. I'll try and draw them as close as I can to their original form. Here's my u, and here's my v. What if I wanted to take u and subtract v? How do I do that? Well, what you do is this. You start with your vector u. Subtraction means I remove it, so it's you add the vector in the opposite direction. So I come up over here, and this is the kind of the negative of v. And that's what I do. When you take the negative, you just switch its direction. So this becomes my u plus minus v, or simply u minus v. So anytime you subtract, you reverse the direction, do a 180 on that direction, and that'll give you the vector in the opposite direction. Doesn't change its magnitude, it just changes the direction of it. Just like going from the positive 2 to a negative 2, it puts it on the opposite side of the number line. Same thing here, it puts the vector going in the opposite direction, and then you just turn it back into addition. And you can do the same thing, you do v subtracting u. Let's take a look at that one now. That's a little bit different. It's not commutative there. Say, as, for example, I looked at now v and subtract u. So I start with my vector, v over here. So there's my v. And then I'm going to subtract u. So I take u going in the opposite direction. So instead of going up, I go down in this direction. And there's my u. So this would be this is my, minus u, I should say. And then I come over here, and this is my v minus u. Now these have the same magnitude, but they point in opposite directions. So this vector and that vector, they're the same length. This is pointing upwards, that's pointing downwards. So they're not equal, but it's equal to the negative of that. So subtraction is not commutative, but addition is. Okay, so we did addition, subtraction. But what about multiplication? Well, this is where life gets a little bit complicated and dicey. There are, in fact, 4 types of multiplication that you can perform on vectors. And this is what kind of life becomes crazy. So if I look at multiplication, there are 4 ways to define multiplication. We're only going to look at one way in here. If you go on, you will see any. I'll list them all just so you can kind of see them. The first way is very simple. We're going to call it scalar multiplication. This is going to be the one we're going to talk about. That. Then there's another one which we won't talk about called the dot product. Also called the inner product. Third way is something called a cross product. And then the fourth way is called an outer product. Now it's interesting, they each yield different things. A scalar product, multiplying a vector by a scalar, will give you, in the end, you end up with a vector. So the result of doing a scalar multiplication is another vector. A dot product, when you do a dot product, you don't end up with a vector anymore, you end up with a scalar, a number. A cross product, this is multiplying one vector times another vector, you get another vector. Now this outer product is even more strange. What do you get? A matrix. Or really, something called a tensor, if you want to go into Einstein's theory of relativity and understand that, then you're dealing with outer product. For us, it's just going to be this simple scaling the vector, multiplying by a single number. So let's take a look at simply scalar multiplication. These other two you will see very quickly in your other courses. So what do we mean by scalar multiplication? Scalar multiplication is simply multiplying a vector times a scalar, a number. So let's take a look. Say we'll start with our vector, v over here. And then if I multiply by some number between 0 and 1, it's say a half or something, it'll shrink it down. So here I have my original v vector. Here's my v vector. But if I multiply by something between 0 and 1, it keeps the same direction, but it now shrinks it down. Now if I look at something greater than 1, so let's take a look at a greater than 1. So I start with my vector v, and if I multiply it a times v, so it's going to look like an even longer vector. But it's still a vector pointing in that direction. And we've also just seen if I multiply it by a negative, it'll change its direction. So then if a is negative, it flips its direction. So, for example, say a is equal to a -1. I start with my v over here, and that will give me a vector going the opposite direction, and that is the negative of v. Okay, so we now know how to work with vectors defined geometrically. The hard part of that is it's not as useful. So there's another alternative definition of vectors, and this is the algebraic definition. Meaning we put the vectors on a coordinate system. For us, we're going to start with the Cartesian definition. In this case, we're going to use that same kind of ordered pair mentality, but a little bit different than that. So a vector is defined algebraically as a directed line segment from a point A, B to B. As a directed, same as we do geometrically, line segment from point A to B. Only now we're going to be putting it on or within a coordinate system. And we're going to just stick with the Cartesian coordinate system right now. So here it is. We now plug it into our Cartesian coordinate. Now we get away from the strict, more analytic geometry than anything else. So this might be point A, and let's say this is my point B over here. So here's my vector defined as my point A to B. But then what do? Well, we break it down into two components. When I look at an angle, I want to go up over here, so I want to be over here. That's where I want my B at. Try and keep it so at least get something a little bit different over here. There's my vector. I'll call it vector V. Or if you wanted to, vector A, B. Those are the same. It's giving a single name. This defines its beginning point and end point. What comes first is the beginning point. What comes second is always the end point in the vector. And what we can do is we have two components. We can then break this down, just like we did, back to Pythagorean's theorem again. We can break this down here, and we call this the x component of the vector. So that's equal to 2 units. This over here would be the y component of the vector. And you can count 1, 2, 3, 4 units. And we can use that to write our vector v, if we wanted to. And instead of using parentheses, we use these angled brackets. Angled brackets represent vectors, as opposed to a point. And then you put your x component, always the x component first, comma the y component. So this vector here, I can see this example that I have over there. That vector v could be represented by 2 in the x, positive 2 in the x, and a positive 4 in the y. Now I'm doing it algebraically. I have numerical quantities associated with both of those. Let's say I had another vector here. Let's say I had another one that went from here to here, and they say that's my vector u. That would be minus 3 in the x and minus 1 in the y. Okay, those are my vectors. Now, when you want to do arithmetic with these vectors, it's so much easier. the last 2 minutes we have over here, or 3 minutes. So the arithmetic with algebraic vectors, if you do addition, and you want to add, say, vector v is that 2 comma 4, and vector u is equal to -3 comma -1, then v plus u, I just add the components together. So it's 2 plus that -3, 4 plus that -1. So it's equal to, that vector is -1 comma 3. And that's the vector. Subtraction, you just subtract the components. So there's addition, and there's subtraction. Then take, u minus v. Well, I start with my vector u, which is equal to 2 comma 4, and I'm subtracting this vector -1 comma 3. So I subtract each component. So it's 2 minus a -1 comma 4, subtracting 3 over here. Oh no, it's supposed to be -3, -1. Excuse me. I'm rushing here, so it's 2, 4, and -3, -1. So this is -3 and then minus a -1. So over here, this would give me 5 comma 5. And just do it component by component. Now, we also can define the magnitude. Well, I'll end here for now. And we'll kind of approach some more of this when we get back from the Thanksgiving break. We can kind of see if we are in our coordinate system, and if I bring my vector down to the origin, this is my x component, here's my y component, make a right angle. The length of that vector is magnitude of vector u, and we're going to define it like this. It looks like absolute values, but it really means magnitude of u. It's defined as the sum of the squares of those two components. So Pythagorean's rule again, x component squared plus the y component squared. So in this case, the magnitude of u would be the square root of 4 plus 16 plus the square root of 20. Oh, excuse me, the square root of u would be 9 plus 1 square root of 10. And that's all it is. And it's written in this notation. Next time we're going to start now. So we're going to be looking at an application called static equilibrium from 10.4. Thank you for alerting me to that. Now, most of this is in the textbook. I'll be following that as well, and the drawing looks a little bit better. But let's show an example from the textbook and what we mean by that. And this, I'll go to the book and then I'll summarize the important aspects of that. Okay, here's out of the textbook. And it's something called static equilibrium. And the idea is you take, in this case, we have an I-beam here, and you have a weight hung from it. And the weight causes these tension in these metal rods, if you will, or metal cables, if you will, that extend from it. And they form an angle. This is an angle on the left of 35 degrees. There's an angle of 50 degrees. And you have a weight of 370 kilograms. What it's going to do, it's going to cause tension in this rod or cable 1 and tension in cable 2. And those are labeled T sub 1 and T sub 2. Now if I take a look at that, what do? Well, we break it up into triangles, right triangles, the right triangle trigonometry, we're back to that as well. And you have your weight that's hanging. Well, how is this related to vectors? Well, what happens is that there is a total of vector forces. Remember, a vector can be used to represent a force. It's a magnitude and a direction. If I break this down, you can see you have this sort of configuration. I have this vector T1 over here. I have another vector T2, and then I have another vector which is the gravitational weight that is, pulling down on those two cables that are attached to that I-beam. So this is really vectors we're dealing with. When every time we have anything in static equilibrium, because it deals with forces, and forces are represented by vectors. So that's going to be what we're going to be looking at to do, is to take and from this picture, original picture here, construct a vector going along T sub 1, a vector going along T sub 2, and a vector going straight down due to the force of gravity. And that's what static equilibrium is about, is when gravitational forces act on things and we can represent them easily with vectors. Okay, so then how do we solve such a problem? Well, it turns out very simply. Let me go back and then we'll come back to this in a second. And it turns out in static equilibrium, it is the following condition holds. This is an important condition. Important condition for static equilibrium. The first is that the sum of the vertical forces has to equal 0. Forces must be 0, because if it's not 0, then it's not in equilibrium. It's moving. Must equal 0. So this is a vertical force, and that's vertical force. They have to be the same magnitude, and the direction is just the vertical. So if this is, magnitude of this is A, the magnitude of that also has to equal A, although the vector is in the opposite direction. So this might be vector, V or something, pointing straight up. Down here, this would be the vector minus V. So the sum of the vertical forces must equal 0. In a similar fashion, the sum of the horizontal forces must equal 0. Otherwise, if it's not 0, then it's moving. There's one force that's dominating over another. So the sum of the horizontal forces must equal 0. So we have a vector going horizontally this way and a vector horizontally this way. They're both magnitudes have to be the same. And I'll put this as V again, maybe U. I'll put this as U. And this could be, in this case, that's the negative of U, and this is a positive U, if you will. Positive, assuming that the signs. They must equal 0. So how does that help us? Well, what we do is we take the picture and you construct that vector equivalent of that picture. So this is what we've done. For that example, in the static equilibrium world. So you go from your picture to this sort of vector over here. Now, the picture is there. I'll set it up here, and then I'll show you how we got the various quantities. So we have one vector that's forming this along cable T1, and we say that goes in this direction over here. Here's another one over here, and this is T sub 2. I can make it go to the same top over here. That's the vector. And we have the weight of the object pulling everything down. That creates another force vector in this direction, 370 kilograms. And then we have some angles that are associated over here with everything. This angle happens to be 55 degrees, and we'll take a look at how we got that. We have 35 degrees over here for this angle. And we have a 40-degree angle over here, as well as a 50-degree angle over here. Okay, where did we get that from? Let's just kind of take a look at the original problem so we can figure out how do we get that set up. Let's go back to our sharing of our screen again. Okay, initially for our problem, we see this is 35 degrees here. Well, we know this 35 plus whatever is remaining here has to be 90 degrees. So we take the 35, subtract it from the 90, and that gives me 55. 55 and 35 is 90 degrees. Similarly, this is 50, that must be 40. Well, if this is 55, we know that the sum of the interior angles of any triangle add up to 180 degrees, that must be 35. We also know that if a line intersects another line, then the opposite angles are the same. So if that's 35, that must be 35. You can do either one of those techniques. So I'm breaking everything up into degrees. So this is what I have. That's why that's 55, 35, 50, and 40. So those are my three vectors that I have. Okay, so what does it say? The sum of the vertical forces has to be equal to 0. Well, sum of everything has to be 0. So let me just put that up here, and we'll kind of do that step by step over here. So what it says to be in static equilibrium is that the vector sums has to be 0. So static equilibrium, and that is broken into vertical and horizontal components. So if something is not moving, it's static, and we call that static equilibrium. And that simply says that if I take the sum of all those vectors, t1 plus t2, that has to equal that other vector, which is by 306, that vector, 370 kilograms. That's a vector that's forcing the weight down for gravity. What do? I break this up into, like I say, the horizontal and the vertical components of everything. But the angles here are a little bit different now. We have this picture over here, but let's see how we then go from here, which is this, which is my equilibrium condition, to breaking that up into different pieces. So let's take a look at the vertical part of it, the vertical components. So these are vectors, and the verticals have to cancel out, and the horizontals have to cancel out. They have to be equal and in opposite directions. So let's take a look at that. So if I'm looking at this picture over here, I want to look at the vertical parts of these triangles. So this angle here, I got to be careful because I have to take a look at, remember, I'm going to reference everything. This is my reference side. That's going to be my reference side. So this angle here will be 50 degrees. This angle over here, however, would be 145 degrees. That's the angle. I'm not going to use this over here because that's pointing in another direction. So it's all going to be referenced to one side, and there's our reference side along the horizontal. Okay, so we have different components of this. So I'm looking at this component here, that component of T1, that vector, and this component of T2. Those two have to sum up to this vector here. So what does this equal to? Well, I can simply rewrite this as, start with this one. This is the magnitude. I'm going to take the length of this, the magnitude of T sub 1, take that vector. And if I want to go in this direction over here, that's going to be my sine of, 145 degrees. Remember, the sine is the SOHCAHTOA times the sine of 145 degrees. That's going to give me this component over here. And then I also have this other vertical component over here. And that's going to be the magnitude of the length of this vector, which is its magnitude. So it's the length of T sub 2 vector times the sine of 50 degrees. So that's in the vertical component, and that has to equal this is pure vertical. So it has to equal the opposite of that. So that has to equal 370 kilograms. Notice these are not vectors anymore. That's a magnitude. This is a number, that's a number, and the sine and cosine and sines and sines are both numbers. no longer a vector. We went from the vector to the vertical component, so this has to be true. Because I don't know what T1 and T2 are. That's what I'm going to want to find out. How much tension? Do I have cables that will support that tension, or will they snap? Then we look at the horizontal components. So the same sort of thing happens now, but now I have the cosine. Remember the sine, it takes me to the vertical, because it's taking a look over here. The sine, if you kind of take a look at the sine as the opposite of the hypotenuse, if you will. So that's the thing we're doing, the opposite of the hypotenuse, and that's why we get that. So for over here, we have that the T1 in magnitude times the cosine will give me my horizontal. That's the cosine of 145 degrees plus the magnitude of T2 times the cosine of 50 degrees. What must that equal? That has to equal 0 since it's not moving. So the horizontal forces, these things balance each other out. So this magnitude here and that magnitude here must be equal. If one is not, then it's going to shift from one side to the other. So, okay, let's put that in. Cosine of 50 degrees has to equal 0. So that's what you do. And you reference one side. Now, don't put sine of, if you put sine of 35 degrees, you have to be careful because it's not going to be so bad for this one, but it's going to be bad for this one because the cosine of 100 will give you negative, and it's going to cancel. It's going to kind of give you the opposite sign. So you have to be careful. Pick one reference angle. So what do we have? After all this, this is a system of equations we have. So let's get rid of the picture for now and see what we're tasked to do. So we have a system of equations, 2 equations and 2 unknowns, and it looks like this. I have my magnitude of t sub 1 times the sine of 145 degrees plus the magnitude of t sub 2 times the sine of 50 degrees is equal to 370 kilograms. My second equation is the magnitude of t sub 1 times the cosine of 145 degrees plus the magnitude of t sub 2 times the cosine of 50 degrees is equal to 0. My unknowns are t sub 1 and t sub 2. The easiest way to solve this is the method of substitution. So we're going to solve by substitution. Meaning I can solve for either T1 or T sub 2 here in magnitude and plug it into there and solve for that and then go back to this. So let's turn around over here and let's go through this. Setting it up is the hardest part. After this, it tends to be a little bit easier. So let's take this one and solve this for the magnitude of tension in vector t sub 1. So here's equation 1, equation 2. So let's solve 2 for t sub 1. So I'm going to move that over and divide by that. So I get t sub 1 is equal to the negative of t sub 2 in magnitude, cosine of 50 degrees, and then I divide by the cosine of 145 degrees. I just move that over and divide it by the cosine. Now I take this and I substitute this for t sub 1 over here. So let's do that. So my t sub 1 now looks like the negative of the magnitude of component t sub 2 times the cosine of 50 degrees over the cosine of 145 degrees times the sine of 145 plus t sub 2 in magnitude times the sine of 50 degrees is 370. I'm going to drop the kilograms for now because we know that. Now notice I can factor out a t sub 2. So let's do that. And since this is negative, I'll put this one first. So that gives me, in this case, I have the sine of 50 degrees, okay, minus cosine 50 degrees over the cosine of 145 degrees, okay. Factor that out. All right, did I get everything? And then I have another sine over here, sine of 145 degrees. Yeah. Make sure the algebra is okay. You got to be careful with your algebra. And this is equal to, in this case, 370 kilograms. Now, pull this factor out of both of them. And I put this first, and then this is the second with a negative in front of it. I can now solve that for the t sub 2 by dividing by this. So in this case, I get my tension in cable 2 is equal to 370 kilograms. My units are going to be kilograms when it comes out, dividing by this. So I take the sine of 50 degrees, cosine 50 degrees. Now, I could put decimal approximations for these at any time. I'm leaving it precise right now, but you could have changed earlier if you don't want to look at all the numbers over here. And when I plug that into a calculator, I'm going to get that my magnitude of my vector t sub 2 is approximately equal to 304.24 kilograms. 304.24 kilograms by plugging into a calculator. Now, once I know what that is, I take this result and I substitute over here. And you're going to see this is the cosine is going to be negative. So this is negative is going to cancel with that negative because at 145 degrees, the cosine is negative. If you didn't do it correctly, you might have gotten the magnitude being negative. But when you plug everything in over here, you're going to get your magnitude of t sub 1 is equal to approximately 238.74 kilograms. And that's all it is. So the cable that you have for 1 and 2 have to be able to withstand that much stress. And you usually want to have it much larger than that because you don't want anything snapping because that weight could fall on somebody below and kill them. But that's a static equilibrium. And it's all dealt with using vectors and the horizontal and the vertical component of vectors. The magnitude over here, that's the length, which is the magnitude of the force that's in that vector. So that's all it is. It's something you have to practice as, you know, some problems in the textbook. Follow the example I have, and it should not be that hard. It always follows the same process and procedure. Now, in this course with statics in equilibrium, they may have several different forces, so it can get much more complicated than this. But that just wanted to show you an application of vectors that you will see, especially if you have to take a physics course or something like that. You will see some of these worked out. Okay, so that's all of chapter 10. Okay, so as I said, I've finished that static equilibrium process up. So now we move on. And the second to the last chapter, this is kind of the bulk of what you would see in a pre-calculus course. This is something you will see less in a calculus course. This is the bulk of what you would see in a calculus course is going to come up right now. And the analysis we're going to do with that. And that's all about chapter 11. And chapter 11 is all about graphical analysis of functions and a little bit of the model. So chapter 11 is graphical analysis of functions.
Professor, You didn't
Yes.
go over the part of 10.4 with the I's and the J's. The
Okay.
section
Yeah.
before the
Okay.
static.
Yeah. Yeah. It's easy enough. Let's do that quickly. But
Thank you.
that shows you how the vectors are. So if you want to look at the I's and J's, and these are considered the special vectors. Sometimes we call them unit vectors. They're also called the what's the other word we use for those? Now the I and J's, I don't mean I in the real and imaginary. I means something different. That's why it can be some confusion for some students. We want to call those, yeah, standard vectors. So let's talk a look about the standard vectors. Well, we have one notation of a vector. So we have a notation of a vector that looks like this. We have vector v, which has and I'm using these kind of like these special brackets there, which is the x component, comma the y component. Well, another way of writing this is as follows. The vector v could be broken up where I have my x component and a little vector, and it's a little vector I, and I'm going to put a little hat over that. The reason I put the hat, I'll show you what that is. That just means that is a vector that has magnitude 1 and has the direction along the x-axis. I can write it like that, or as a y component and a little vector j. Well, what are these? Well, if I look at my xy coordinate system, the I vector over here, if this is of length 1, will point in this direction. That's the length. The hat just means it only has length 1. The j vector is perpendicular to that. That also is 1, but it points in the upwards y direction. So, for example, if I have the vector, in this case, vector v is equal to 2 comma negative 3 in my vector form, vector component form, I can also write that, if I wanted to, as simply 2 in the I direction, 2 times a vector in the I direction, plus 3 times a vector in it. So it would be 2I and 3j. It would be a vector, or minus 3j, excuse me, minus 3j. Let's show you what I mean by that. So let's draw that vector in my grid system over here. So what does that vector look like? Well, it goes 2 units this way and down 3 units that way. So that is my vector v drawn over here. But over here, it's like adding or subtracting 2 vectors. It takes the vector 2 in the I. This is the vector, that is just 2 in the I direction. Okay. And here's 3 in the j. Well, if I go 3 in the j, I'm up here. This is 3 in the j. But I'm subtracting. So what do? I flip it down when I'm subtracting. So it becomes down here. And this is minus 3 in the j direction. Notice it gives me the same vector. And this uses the ij. Now this I has nothing to do with the imaginary number I. And in fact, if you take anything like an electrical engineering, you will see this I becomes current, so then they use J, and it gets all sorts of confusing. But we use the I symbol to mean 2 different things in this context. One is a vector, it's the component along the x-axis is the I, then J is the component along the y-axis. And then how do you add and subtract? The same thing. If I'm adding 2 vectors, so say this is vector v, and I have a vector u, which is, 4i plus 3j, and if I want to add u plus v, I just add the I and j parts, the x components and the y components. So it gives me 2 plus 4 in the I direction, plus, 3 minus 3 in the J direction. So this just gives me a 6 in the I plus 0 in the J, which I can just write as 6 in the I direction. I can just drop that. There is no J component. This is all horizontal. Or if I wanted to write that in my vector form, it's 6, comma 0. That's all it is. Just another alternative way of representing a vector. It means the same thing as this, but now we use ij. And then, for those of you that go on to calculus 3, we then go into x, y, and z comes out of the board, and then we go I, j, and k coming out in the direction. So we extend vectors into three-dimensional vectors. From two-dimensional here, calculus 3, everything switches over to three-dimensional vectors. We do a lot with two dimensions, but we do a lot in the three dimensions. But that's all. These are the standard vectors. Sometimes we also call them the unit vectors because they have magnitude of 1. If I take the magnitude of 1, they look like this. And here's another way of interpreting it as well. We also have that vector I has components 1, comma 0, and vector J has component 0, comma 1. Written in the other alternative form. So that's all it is. So that's not too difficult.